Hi everyone, today we're going to be discussing the second FRQ of the 2017 AP Chemistry exam, which mainly talks about rate and equilibrium and structure. This question asks us to look at formal charges. So let's first of all denote the formal charges for each atom in every molecule. Let's look at hydrogen first. Remember that the formula for formal charge is valence electrons minus bonds plus lone electrons. And that'll come in handy here. So we look and we know that hydrogen usually starts out with one valence electron. So we're going to put one there. And then in the first molecule, we see that hydrogen only has one bond and no lone pairs. We subtract a 1, we get 0. In the second one, the same thing. Hydrogen has one bond and no lone pairs. So hydrogen doesn't differ. Now, let's look at carbon. We know that carbon starts with 4 valence electrons, which is why it makes 4 bonds typically. So we see in the first molecule that carbon has one single bond there and a triple bond there. So carbon has a total of 4. So we subtract 4 and we get 0. Now, let's look at the next one. We see that carbon has a single bond on the left, a double bond on the right, and 2 electrons here. 2 plus 1 plus 2 equals 5. So we subtract 5 and we get -1. Now, let's look at nitrogen. Nitrogen, we know, always starts with 5 valence electrons. We see here that nitrogen has a triple bond on the left and a single bond on the right. 3 plus 1 is 4, so we get that nitrogen's formal charge in the first one is +1. Now let's look at the second one. We have the same thing here, except we have double bonds that are split. So we have 5 minus 4 again equals +1. Now let's look at oxygen. This one will probably change. We know that oxygen starts with 6 valence electrons. We see here that we have 6 electrons from lone pairs and 1 single bond. So 6 plus 1 is 7. We're going to subtract 7. We see that oxygen's formal charge is -1. Let's go to the second. We see that oxygen has 4 electrons from 2 lone pairs plus a double bond, so 4 plus 2 equals 6. We're going to subtract 6 and we get 0. So we see here that we have carbon has a -1 here, but oxygen has a -1 here. Remember that we always want our more electronegative atoms to have the formal charge, and we want the less electronegative atoms to always be 0. So our answer is going to be that carbon has 0 formal charge in the first molecule, but -1 in second. Oxygen has -1 formal charge in first and 0 in the second. The first is better because of oxygen's formal charge, and you will go on to explain that you want your more electronegative. Right here, we are given our 2 different forms of acid. We have fulminic acid, in which the hydrogen is connected to the carbon, and we have isocyanic acid, in which the hydrogen is connected to the nitrogen. So, we're being asked to calculate the change in enthalpy based on bond dissociation energy. Remember that when you're doing bond dissociation energy, you have to subtract from the bonds broken minus bonds formed. In other words, we're going to be doing reactants minus products. Alright, now let's look at our versions for each of them. So we see in the first one we have a carbon-hydrogen single bond, and according to our table that's going to be 413 kilojoules. Now next we have to add to that a carbon-nitrogen triple bond, and we see that CN right down there is 891. Next we see that we have a nitrogen-oxygen single bond. The value of that, 201. Alright, when you add that all up, you get that the bond enthalpy of our reactants total is 1505 kilojoules. Now, let's look at our products. First thing we have is an HN single bond, so that's going to be 391. Next thing we have is a nitrogen-carbon double bond, that's going to be 615. Finally, what we have is a carbon-oxygen double bond, which is going to be 745. When we add all of those up, we get 1751 kilojoules. All that's left is we take our 1505 kilojoules minus our 1751 kilojoules. And we get a total of negative 246 kilojoules. That will be our change in enthalpy. And if you think about it, it makes sense, because here you have nitrogen in an unideal place with 4 bonds, and in the next one you have nitrogen in a more ideal place with 3 bonds. Carbon has 4, oxygen has 2, and everything is happy and more stable compared to fulminic acid, so it makes sense that you would have more negative. So we have to agree with the student's claim here. We're not given an option. Let's think about what entropy changes. Entropy changes if you have a change in state, or if you have less or more particles. Here we have neither. We know that they're both in the gas state, and we're not changing the number of particles. So we have to say that the student is right, because there's no change in state or number of particles. And that's really all you need to say for this question. It kind of explains itself. For this question, we see that they ask about thermodynamic favorability, which is delta G, and the equilibrium constant, which is K. We know that entropy, which is S, pretty much equals 0, and we know that our delta H is negative. Therefore, delta G will also be negative. And so we know that if delta G is negative, the reaction is spontaneous. And if the reaction is spontaneous, then we can say that the products are favored. Our last thing that we need to say is that if products are favored, then K will be greater than 1, because you'll have your product over reactants ratio. In this question, we are given a new equation with some ammonia compounds. We see that we're studying urea as a function of time, and he proposes that the rate is first order as seen here because there are no exponents, so we assume an exponent of 1. We are asked to explain how the data supports the student's proposed rate law. We know that if you have a rate law with an order of 1, concentration versus time is going to be 1 over concentration equals time. Or the other way around, if time is the independent variable, 1 over time equals concentration. And we see here, and that would create a graph something like this, right? You'd have like a little 1 over x kind of graph. And we have that exact thing here. So we can say that he says that the rate, or not that the rate, that the order of CONH2 is first. And the graph is 1 over x with the slope. So that confirms that it's first order, because if you have a graph that has the slope of 1 over t as a concentration, and you have a graph of time versus 1 over concentration, then you will get a straight line with. Since this reaction is a first order reaction, we can use our radioactive equations. We know that K equals 0.693 over the half-life. Now first of all, we have to find the half-life. We see that we start at 0.10 here and we have 0.5 here, and that takes exactly 10 hours, so our half-life is 10. We do 0.693 over 10 and we get that our half-life is 0.069. But we need to find our units for K. To find our units for K, we take our overall reaction order and then we subtract 1. Our overall reaction order, we only have one reactant, which is this, and we figured out that it was a first order reactant. So we have our, remember, is 1 over molar times the time unit, which is hours, and then we put the molar to the power that we have. So we have 1 over molar to the 0 because we have first order minus 1 times hours. Therefore, that's just going to come out to 1 over hours, and that's our unit. So our final answer is 0.069 hours to the negative 1. This final question, we are asked to consider the pH. We learned that decomposition reaction had a pH of 13, and we're trying to find how the reaction depends on the concentration of the hydroxide ion. So we need to keep all factors except for concentration of hydroxide constant and collect data. Because by keeping all other factors except for the concentration of hydroxide constant, we're only changing the pH, and so any change that happens as a result of our different trials will be only due to the pH and nothing else.